In this example, we have a linear equation, the left-hand side of which is 1 plus x squared, that quantity times dy dx, plus 2xy. Because y appears as nothing more interesting than itself and its derivative, this is linear. F of x on the right-hand side, though, is a piecewise defined function where f of x is equal to x as long as x is between 0 and 1, inclusive at 0, and negative x when x is greater than or equal to 1. Note we also have an initial condition, y of 0 is equal to 0. And in a case like this, we end up having to deal with the differential equation twice. Once on the interval for x between 0 and 1, again inclusive at 0, and once on the interval for x greater than or equal to 1. In both cases, we need the equation in standard form, so we've got dy dx plus 2x over 1 plus x squared y is equal to, and in the case of the first interval, the right-hand side is x over 1 plus x squared. And in the case of the second interval, we have negative x over 1 plus x squared. Since the left-hand side is the same for both, we get the same mu. Mu is equal to e to the integral of 2x over 1 plus x squared dx, which is going to give us e to the natural log of 1 plus x squared. And so mu is equal to 1 plus x squared. Rewriting the left-hand side of the first equation gives us the derivative with respect to x, or d dx, of 1 plus x squared times y. And then we've got to multiply that 1 plus x squared on both sides. And so that derivative of 1 plus x squared y is equal to x. In the case of the second portion of the interval, where x is greater than negative 1, so the right-hand side is negative x, everything about the left-hand side is the same, the derivative with respect to x of 1 plus x squared times y. And then on the right-hand side, we end up with negative x. Now these are only differing by a negative, but there's nothing that says that this has to be the case. These could be drastically different, in which case we would have basically two separate processes on the right-hand side for integrating. Because remember, that's where we're going to go next. We're going to integrate both sides with respect to x. And I'm doing these kind of left and right simultaneously here, but it would also be just fine to take the first one as far as you can, and then take the second one and move forward from there. In the case of the first one, we have 1 plus x squared times y is equal to 1/2 x squared plus c. And so y is equal to, I'll say, x squared over 2 times the quantity of 1 plus x squared plus c over 1 plus x squared. Now remember, this was the case where we had x between 0 and 1, inclusive at 0. For the portion on the other interval, we still have this 1 plus x squared y, and we still have, well, I guess in this case it's negative 1/2 x squared plus a constant integration, but there's nothing that tells us that we should expect the same constant of integration. So over here I'm going to call it d instead of c. Then we have that y is equal to negative x squared over 2 times 1 plus x squared plus d over 1 plus x squared. And again, this applies when x is greater than or equal to 1. Because this was an initial value problem, we're going to be able to find our constants, but the initial condition only applies to when x is equal to 0. Right? We have y of 0 is equal to 0. If x is equal to 0, then the right-hand side was positive x. And so the initial condition only applies to the solution that we had for x between 0 and 1, inclusive at 0. And you can see that if x is equal to 0 and y is equal to 0, that gives us that c is equal to 0. So we have the solution y is equal to x squared over 2 times the quantity of 1 plus x squared, on the interval between 0 and 1 inclusive at 0. We don't get to use that same initial condition to find D because D was associated with a solution that was only good for x greater than or equal to 1. Obviously, if x is 0, x is not greater than or equal to 1. I'm going to go back to the instructions here, and we were told to expect a continuous function. Now, you might recall that f is continuous at a if the limit as x approaches a of f of x is equal to f of a, and the limit as x approaches a of f of x exists if it's the same limit for x approaching a from the negative side and x approaching a from the positive side. In this case, our split happens at 1, and we have one definition of f to the left of 1 and one definition of f to the right of 1. So we need the limit as x approaches 1 from the minus side of f of x to equal the limit as x approaches 1 from the positive side of f of x. What that means for our solution is that we need x squared over 2 times the quantity of 1 plus x squared to equal negative x squared over 2 times the quantity of 1 plus x squared plus d over 1 plus x squared when x is equal to 1. Substituting 1 in place of x is going to give us 1/4 is equal to negative 1/4 plus d over 2, and we'll find that gives us that d equals 1. Putting it all together, y has a piecewise solution. For the interval from 0 to 1, inclusive at 0, we have x squared over 2 times 1 plus x squared. For the interval to the right of 1, we've got our other definition, or other solution, I should say, which is negative x squared over 2 times the quantity of 1 plus x squared plus 1 over 1 plus x squared. We include the intervals because we have a piecewise defined solution. In the instructions, we were asked to graph the continuous function, and you can see we have 2 definitions for our function, one on the interval from 0 to 1, one for x greater than 1, and we can see that this is indeed a continuous function.